All right, welcome to Unit 3.1, Section 3.1. Unit 3 is all about functions, the basics of functions, and some weird things that happen with functions. Unit 3 is really a setup for Unit 4. So if you look at it that way, I think it might be a little bit easier to kind of wrap some of these ideas and see where they fit in the big picture. So we're just going to discuss functions, and here 3.1, this is going to be relatively easy. And then we're going to get into more of how functions, how we write them, how we use them, how we can do different things with functions and function notation. All right, so our goal for 3.1 is to evaluate functions from a graph, table, or a function, okay? And so the first thing I want to do is I want to take a look at what is function notation. Sometimes it's good to take a second and say, what in the world is it that we're doing, and why are we doing it? And I sometimes like to take a look at Google definitions. So the shortened version of the Google definition, so the Google definition for notation. So notation. What is the word notation? And this is what Google sends back. It says a series or system of written symbols. It goes on to say that it's most often used in math. And this is kind of it. We're going to use symbols to describe a function. Okay? All right, so here we go. Function notation is function notation. It's f of x equals, and then in general we have some sort of a rule on the right-hand side, on the other side. And I want to get you used to this, what it means and how we say it. So shorthand, we're going to say f of x. That's shorthand for what we say, f of x. F of x. But in math, what we're really saying whenever I see this, what I'm saying in my head is the function f, because it's f, evaluated at x. So the function f evaluated at x. So this is what I'm really saying. In shorthand, so this is shorthand, right? So this is the quick and easy way we say it. But the true meaning is the function f evaluated at x. All right, so that means that we could also evaluate f at other things too. So there's something else that I could do with this. Really, f of x itself is y, right? And this is the output of the function, where x is the input. So notice here, I'm actually the function notation itself uses the input already. And one thing I really need you to understand, this right here is not multiplication. Okay? I can't tell you how many people I've had to tutor and say this is not multiplication. It's notation. How we say what we say. How we say what we say. So f of x, all it really is the y value. It gives us a little bit more flexibility, right? In general, we want to say a whole lot using very little. So let's take a look at what we're going to see in some of our examples in the homework. All right, so here we have f of x equals 3x squared minus 2x plus 7. If we didn't have function notation, I could write this as y equals 3x squared minus 2x plus 7. But then I'd have to say something like, what is the y value when the x value is -3? It's just so much to say when function notation just simply says, hey, replace x with -3. Okay, I could do that. Replace x with -3. And then we could simplify from here, right? So -3 squared is 9, so then I get 3 times 9. -2 and -3 is a plus 6 plus 7. So 27 plus 6 plus 7, that is equal to 40. All right, so f of -3 is 40. This corresponds, if I were to graph this thing, the x value here, so the x value is -3, the y value is 40. So this corresponds to the point on the graph, -3, 40. Now what happens when I plug a 0 in? Well, I would do the same thing. 3 times 0 squared minus 2 times 0 plus 7. 0 minus 0 plus 7 is 7. And that corresponds to the point 0, 7 on the graph. And what happens when we plug a 1 in? All right, 3 times 1 squared minus 2 times 1 plus 7. Well, 1 squared is 1. 3 times 1 is 1. Oh, excuse me, 3 times 1 is 3. Let's write that down. -2 times 1 is -2 plus 7. 3 minus 2 is 1. 1 plus 7 is 8. So that corresponds to the point 1, 8 on the graph. The big thing that I really want you to take away from this is whenever I use function notation, whenever I replace this, the x, with whatever this is, I got to replace all of the x's in the function. And then I just use PEMDAS. Now, you guys done a plenty of work when it comes to order of operations, so I'm not real worried about that. All right, let's take a look at another example. All right, it wants to know f of -4. All right, here's f of x. F of x, and the rule on this one, f of x is the square root of x plus 4 minus 3. So I'm going to start in by plugging in the -4. So I get -4 plus 4 minus 3. And I want to use parentheses. I replace x with parentheses, and then I plug the number in. That's going to come in handy whenever there's a negative or something like that. All right, well, -4 plus 4 is 0, and the square root of 0 is 0, and 0 minus 3 is -3. So this is the point, -4, -3. The x value is -4, the y value is -3. All right, what happens when I plug a 0 in? All right, well, 0 plus 4 is 4, so then I have the square root of 4 minus 3. Well, the square root of 4 is 2. And so I get 2 minus 3, which is -1. Let's plug a 21 in there. 21 plus 4 minus 3. 21 plus 4 is 25. The square root of 25 is 5. And 5 minus 3 is 2. So as you can see, all I'm doing is plugging the number in. Let's plug this last one in here. Here we go, -8 plus 4 minus 3. So now I get -8 plus 4. Well, that's -4. And now I need to take a second here. I'm dealing with functions. I'm not solving an equation. I'm trying to find y values. And is there such a thing, a y value? Because I could simply rewrite this as 2i minus 3. Well, that's neat and all, but where's 2i on the y-axis? There is no 2y on the y-axis. So here, this does not exist. So if I catch myself in a situation where I have a square root of a negative number, hey, I can say, hey, this does not exist. Does not exist. All right. Now, what happens when I look at a table of values? This one, it's way easier than what it looks. All right, so remember, what goes in is x and what comes out is y. So here I have x's and y's. So the chart that they gave me are x and y values. So when I plug a -1 in for x, -4 came out for y. When I plug a 0 in for x, 9 came out for y. And when I plug a 2 in for x, 105 came out for y. And that's it. It really is just that easy. So let's try one more example. Pause the video and see if you could get these on your own before I do them. All right, so pause it real quick. Do these 3 questions. Actually, you could probably do them in your head before I'm done talking. All right, here we go. -6 goes in for x, -1 comes out for y. 0 goes in for x, 12 comes out for y. 5 goes in for x, 22 comes out for y. And that is it. Nothing more fancy than that. And the last thing I want to do is I want to take a look at a graph. What happens if I have a graph? All right, so here, this is the graph. The graph that was given here, this is the graph of f of x. They graphed it for me. And now I want to determine if I plugged a -3 in for x, what's the y value that comes back out? Well, let's go to -3 along the x-axis. I go to -3, and I'm looking, what's the y value here? Well, the graph doesn't even go to the left of 0. So here, there is no y value. So this one does not exist. All right, what about when I plug a 0 into the function? Well, here's 0 for x. What's the y value that comes out? The y value that comes out is 3. And what happens when I plug a 4 in? Well, here's 4. Bam, that's the point. Here's the point. What's the y value here? The y value is 5. And that is it. It's just as easy as that.